So today's problem of the day is party in town. Geek town has n houses numbered from 1 to n. So just keep a note of this. It's one index based. They are connected with each other via n minus 1 bidirectional roads. So it's an undirected one. Okay. And an adjacency list is used to represent the connections. Find the house from which the distance to the farthest house is minimum. So from each of the house we need to find the distance to the farthest house from each of the houses. Like if we are having 5 houses, from each of those 5 houses we need to find which is the farthest one from that particular house, and from all those tracked distances which is the minimum one. That's what it's actually asking to do. So let's consider the first example. It's having 2. So this 2, one is having a connection to 2. So one is having a connection to 2. Now 2 is having a connection to 3. 2 is having a connection to 3. Now 2 is having a connection to 4. 2 is having a connection to 4. So what this adjacency list means, consider this is 1, this is 2, this is 3, this is 4. So 1 is having an edge to 2. 2 is having an edge to 1. 2 is having an edge to 3. 2 is having an edge to 4. Now here 3 is having an edge to 2. 4 is having an edge to 2. So this is index base. So let me just explain that also, like 2. Then it's 1, 3, 4. Then it's 2. Then again it's 2. So consider like this one. This is for node 1, and this one is having a edge to 2. Okay, now we are having a 2. This 2 is having a edge to 1. This 2 is having a edge to 3. This 2 is having a edge to 4. Now we have 3. So 3 is having an edge to 2. And we have a 4. And 4 is having an edge to 2. That's what this graph looks like. So that's exactly what this one is. 1 is having an edge to 2. 2 is having an edge to 1. 2 is having an edge to 3. 3 is having an edge to 2. 2 is having an edge to 4. 4 is having an edge to 2. And this is undirected one. Now what we need to do, from each of this, okay, from each of these houses we need to find the farthest distances. Okay, so from 1, which is the farthest distance, 1, 2, 2. So these 2 houses are the farthest house, and this distance is 2. Okay, it's 2. Now from 1, which is the farthest one, this is 1. This will be 1 because only a distance of 1. If you take 1, 2, 3, 4 like incremental way of 1, then this distance is just 1, and this is also distance is 1. So we have distance for this 2 as 1, the minimum one. What is the farthest distance from this 3? It is from 3 to 2, from 3 to 2, and from 2 to 1, and it will be 2. So this is the farthest one, and it is having a distance 2. And from 4 we need to go to 2, then we have to go to 1. It's again having a distance 2. And what is the minimum from all of this? It's 1. So that's what this question is asking. Let's also try another example. So let's say we are having 30 nodes. Let's say we are having 30 nodes, and we are having a edge from 1 to 2. Then we are having a edge from 1 to 3. Then we are having a 1 from 2 to 4. Then 2 to 5. Then 5 to 6. Then 5 to 7. Then 6 to 8. Then 6 to 9. Okay. Then 9 to 10. And 9 to 11. Then 10 to 12. And 10 to 13. So from 1, what is the farthest nodes? From 1, the farthest nodes are 12 and 13. And what's this distance? It's 1, 2, 3, 4, 5, 6. From 4, both of these 12 and 13, we are having a distance of 6. Now from 2, what is the like farthest node and its distance? The farthest nodes are still 12 and 13. And what's this distance? 1, 2, 3, 4, 5. We are having a 5. And this is minimum. So our answer will comes to be this one after updating. So now we have from 3. From 3, which is the farthest one, is 13. Like we can go from 3 to 1, then from 1 to 2, 2 to 5, 5 to 6, 6 to 9, 10, 13. So 1, 2, 3, 4, 5, 6, 7 will be the answer, but it's maximum one. So our answer will not get updated. Now from 4, what is the farthest? It's still 12 and 13. They are the farthest houses or nodes. So we will be having 1, 2, 3, 4, 5 and 6, and that's also we don't want. Now from this 5, what is the farthest node? We have 1, 2, 3 here. Okay, 1, 2, 3 here. Now from here 1, 2, 3, 4. This 13 and 12 is still the farthest one, and we are having the distance of 4 to them. So we need the maximum farthest distance. So it must be the maximum, but from all the different farthest distances we need minimum. So now we have 4, and our 4 will be the answer now. 5 will no longer be the answer. Okay, now let's consider 6. From 6, which is the farthest one, let's have 9, 10, 13. We only have a length of 3 or a distance of 3, but there can also be a possibility that it can go upward. So it will be 1, 2, 3, 4. It's 4. So the distance is 4 itself. So the answer will still be 4. Now we can have 7. 7 is also the same case here. 1, 2, 3, 4, 5. This is the farthest one. Okay, and here 1, 2, 3, 4. Just 4, but this is the smallest one. It's not the farthest one. So the distance is 5, but 5 is still lesser. So it will not be considered. Our answer will still be at 4. Now we go to the next node, say 8. Now we say 8, and what is the farthest one? Let's consider. Is 12 or 13 is the farthest? 1, 2, 3, 4. So here for this path, it's having a distance of 4. What if we go upward? We can go here 1, 2, 3, then 4, 5. That's the farthest one. So we have 5, but the 5 will have no effect because we are looking for the smallest one among the farthest. So the answer for this 8 will be 5, but we need the minimum, so 4 will be the answer. So like that we can do for everything, and the 4 will only be the minimum one from all the farthest distances. So the idea is simple. We consider every node. Then we find the farthest heights, plus we also keep track of the minimum farthest height. So just doing any kind of a traversal, like we can do BFS, we can do DFS. DFS will be more suitable, and DFS will be more suitable, and we can make use of a DFS for this problem. So let's try to do this. So the idea is simple. Like we will be considering every node, then we will be finding the farthest distance from that particular node. We will be tracking that distance. We will be also tracking the minimum distance found so far, and we will be just updating. Like it will be the min of minimum distance, comma, max or the farthest distance of current node, like this. it will the min of minimum distance that we tracked so far, comma, the farthest distance of the current node. So that's what we need to do in this problem. So let's have this smaller. So let's have our minimum farthest distance. So we are just comparing and taking on the minimum. So initially we have to assign it with some larger value. We can give integer dot max value, or we can give n, because it's given there will be only n minus 1 bidirectional roads. So the we can consider it will be maximum n or maximum n minus 1. So the minimum farthest distance we can initialize it as n. Now it's one index based, we need to have a special care for that. So if for we can also have int farthest distance of current is equal to, let's have a new int of 1, because this is pass by value in Java, so we can just make use of a single sized array and just keep on updating. It will be more convenient than putting this farthest distance of current as a global variable. So it's not a good practice, so we can do we can make use of this approach. Therefore we need to visit all the nodes I less than or equal to n, I plus plus. Now what? Now let's say our farthest distance of current. We are yet to start our DFS, so the farthest distance of current is 0. Now do the DFS. So we pass the adjacent, we pass the node, we also keep track of what's its parent. So let's say the parent is minus 1. Then what we needed? Then we needed farthest distance of current. Okay, now we just need the minimum. So minimum farthest distance will be updated as mat.min of minimum farthest distance that we see so far, comma, the farthest distance of the current one. So this farthest distance of current. So that's it, just return the minimum farthest distance. That's it's in the sense like we yet to do the DFS, but this is the logic. From each of the nodes we will be finding the farthest one, and among them we will be taking the minimum. Now only the DFS part is missing, and let's quickly code that. Array list of integer adjacents, then int node, int parent, int farthest distance. Okay, now update the farthest distance. It must be the maximum. And also one thing, like we are starting from the first level, so distance 0, so that's also needs to be tracked. So int current distance. So farthest distance of 0 must be the maximum. Farthest means till the very end, so it will be the maximum from that particular node. So maximum height in the sense if we consider it as a tree. So mat.max of farthest distance of 0, comma, current distance. Okay, we updated our farthest distance. Now just say we need to go through all the children. A list of integer children is equal to adj dot get of node. So for each of the integer child from children, So here we need to add a condition. There is, since this is a bidirectional one, like we can say we start from 1. This doesn't have any parent. This parent is -1 initially. Now we go to 2. So the point we reaches 2. 2 will be the current node and 1 will be the parent. And from this 2, we again do the DFS, and we can go to 4, we can go to 5, we can also go to 1, because this is bidirectional, but we keep track of the parent. So if we see, like if we try to go here, we see that the parent of this 2 is same as the other node. So from this 2, we are having the child as 1, 4, 5. So we check whether this 1 is equal to the parent of 2, is equal to the parent of 2. So we will skip it, and then we go to this 4, incrementing the level. So that's the step that we need to check here. If child is not equal to the parent, then only we continue with our DFS into other nodes. ADJ, the current node will be the child and the parent will be the current node, and our farthest distance is the same, and we go distance 1 down a level. So our current distance increases. Sorry. So that's it. That's our party in town. So there is a compilation error. Minimum farthest distance. I think there is an error. Minimum farthest distance. Oh, let me just copy a large variable name. Yes, there is some error. Yeah, instead of minimum I took minimum. Sorry for that. So new sortable method for min of int. So this has to be 0. Okay. We do this because in Java it's pass by value. There is no pass by reference. So we can just pass an array of size 1, and this value will keep on updating here, and that's what we needed. Otherwise we can make use of a global variable, but it's not a good idea or good practice in order to make use of a global variable. So instead of that, like in Java, we can make use of a single valued array, or this function need to return an integer value. If we don't want to this function to return an integer value, we can just make use of an array of size 1, and this value will keep on updating inside this DFS function, and that's what we needed. And that's the same function which will be done by making use of a global variable also. So here, like we only have the extra stack space, no other extra space we are having. So the space complexity, we can say big of whatever be the stack space, some auxiliary space. For time complexity, like we are passing through each of the nodes, then passing each of this child. So we can say big of n into n. Yeah, big of n into n itself, because we are having n nodes and n minus 1 edges. So it will be big of vertices into big of edges. So big of n into n is the the time complexity and space complexity. There will be some auxiliary space for this stack, because we are doing the DFS. Other than that, like we are not having any extra space. Okay, so that's the problem for this day, party in town.